Good, we get started again. So, as you can see on the next slides, there is the proof of RSA. I will skip it because you really have to study the theory first. But the good news is that you see the proof is only 2 slides, so it's not so difficult. And again, the exam is open book, so nobody has to memorize proofs in my course. I think it can just give you new insights how it works. We'll now look at the question, how big should RSA moduli be? And so we can look for this at records. And so the record, as you see, is from 2020, so it's now 3 years old. It's 829 bits. But we do believe that the NSA can factor 1024 bits. So 829 digits, you have to divide by 3.3, this is 250. So 829 bits is 250 digits, okay? So if you go on the slide here, RSA was proposed in 1977. So before that, people used mainframes to factor 40 digits. And in the 1920s and 30s, mathematicians were factoring using machines built with bicycle chains. And they could do 12 to 15 digits with those machines. But so, of course, then the interest started picking up. And you see a steady progress. But there is 2 things you should remember. First, be very careful with predictions. Because in Scientific American, in 1978, Martin Gardner put a number, a challenge number, and Rivest was quoted as saying it would take 40 billion quadrillion years to break. Okay, now nobody knows what billion and quadrillion means because the British and the Americans can't agree. But apparently it's 4 times 10 to the 15 years. And this was RSA 126. And so he actually encrypted the plain text, which was, the magic words I scream is ochiffrage. And so as you can figure out, it took a bit shorter because it was factored in 1996, 18 years later. So it's a bit shorter than 4 times 10 to the 15 years. So making predictions in factoring is dangerous, okay? So the other thing you should know is that there have been 2 breakthroughs in 1980. A very weird British mathematician, John Pollard, actually found a breakthrough called the quadratic sieve. And then in 1990, he made another breakthrough, the number field sieve. And Pollard is, I don't know whether he's still alive, but he never traveled, he never published anything officially. And if you wanted his papers, you had to write him a letter. And then he said, thank you for asking my paper. Here's a postcard of my city. Can you please send back a postcard of your city? He was a very nice guy, but very weird. But so every 10 years he felt he had to make a breakthrough. But somehow he stopped, luckily for us, in 1990 to make breakthroughs. So there have been no new ideas, really. And all the other improvements we still see improvements, are based on better computers. Faster computers also, of course, from the 90s on, we had massive parallel computers. You can parallelize factoring, especially the first step of it, the sieving pack, you can actually divide over millions of computers. So this record was done, also interesting, was done on PlayStations in EPFL, because at that time was the cheapest computer. They were subsidized by Sony, so you would buy their games, but you could root them, and then they were factoring on them because they were the most efficient at factoring. But so the problem, of course, is academics. If you have to do this in an academic computer, you have to have a team of 3-4 people who work for months or years, and you have to convince your academic management to spend $500,000 or so on electricity bill, plus probably 100,000 on hardware. So, of course, the NSA, they have tens of millions of budget, and probably some other governments as well. So don't believe that because this is the record that NSA cannot do 1024. Okay? So we have actually curves, so there is actually no rigorous analysis, but there is good heuristics where we can predict how the cost of factoring grows for the currently known algorithm. So maybe Pollard wakes up in 2030, if he's still alive, and he comes with a new breakthrough, then all bets are off. But if not, so if all algorithms for factoring have this shape in complexity, big O means there is a constant, and then there is this weird function, which is exponent of b plus O1 times ln n to the power a times ln n to the power 1 minus a. So if a is 0, then this term falls out, or this product, this factor is 1. And then, in fact, factoring is polynomial time, which means it's efficient, which means the cost only grows as a polynomial with the size of the modulus in bits. And then it depends how big b is, how fast it grows. So this O1, it's a way to say this is a constant which is not constant. So b plus O1, it just means that, there is a constant which is not constant. So it can change with n a bit. And you have to do experiments to find out how big b is. That's more or less a polite way, a clever way to say that. But it doesn't grow with n, but it's not constant necessarily. Now, if a is 0, then this term cancels out. And then you have only this term, or this factor here. And then, in fact, factoring with polynomial time, if a is 1, then this term is kept, and this falls out, and then it's exponential. It means it grows. If you double, more or less, the modulus, it becomes 4 times harder. So that's polynomial. So that it actually grows. If you add bits, you multiply the factors. Okay? So 2 to the something. So the interesting thing is that for the best known algorithm, quadratic sieve, in fact, b is 1. The constant here is 1 plus some small constant. And a is 1/2. So it's just halfway between exponential, which is very hard, and polynomial, which is easy. So it's not exponentially hard. In fact, there is harder problems. But it's also halfway. And with this record was broken 129 digits. And then Pollard came, and then the details were worked out. And so currently the best known a is 1/3. The constant b is a bit bigger. It's 1.9. And so this actually has made enormous difference, not only the computer, but also the better algorithm. So it's now 1/3 efficient, 1/3 inefficient, 2/3 efficient. By the way, for some discrete log problem, discrete log has the same curve, discrete log mod p. But if p has special structure, or p if you have p squared, or a small p to a large power, then in fact a can be much smaller and can even be 1 over a very big number. So for this is quite recent breakthroughs from the last 5 years. So for discrete log, in some special cases, a is even smaller, and in fact there is efficient algorithms, and you can compute discrete log over 10,000s of bits. But not for prime numbers, which have no structure. There also the same thing applies. A is 1/3. This is not a proof. This is just what we observe, right? If Pollard has another idea, it can be 1/4. And then factoring would be a lot easier. So again, this is some advice that, 4 to 6 years, maybe 10 years, I'm being pushed all the time because the Belgian ID card had first time 24 bits. Now it has 2048 bits. And I said, yeah, it's probably okay for 5 years, but then they came and say, yeah, we're going to use them for 10 years. Okay, I should probably write 10 years on my slides, otherwise the government is upset. But probably 10 years is still okay. But again, don't only rely on academic things. The NSA is much more powerful. The NSA themselves said 8 years ago, go to at least 3,000 bits. But then they would have to give every Belgian a new ID card, which would be very expensive. Not the card. The card costs only €1 or so, half €1, but all the processes to deal with it and all the software that has to be updated. So imagine that, so you're giving up factoring because you think it's too hard. Maybe we can find lambda n, because if I can find lambda n, then I can actually find d from E and I can decrypt anything, right? So maybe you can find lambda n. Now you can show, in fact, that if you can find lambda n, then you can factor. So this is not a better approach. It's not so hard to prove, although it's too hard for this class. So what I prove is, if you can find phi of n, then you can factor. What is phi of n? Phi of n is p minus 1 times q minus 1. Okay, so lambda n is least common multiple of p minus 1 and q minus 1. Phi of n is p minus 1 times q minus 1. Okay? So if you see this, you see that lambda n is always a bit smaller than phi of n, because p and q are odd. So there is always a factor 2 in common that cancels out. So lambda n is always 1 bit smaller. So in easy classes, people actually define RSA with lambda n. So you could also put right here phi of n, sorry. It also works, but then your secret exponent is at least 1 bit more. So you will not do this. In practice, you will use lambda n. Okay, so I will now show you if you know phi of n, then you can actually factor. Not so hard, because if you write n minus phi of n plus 1, well, that's p plus q, because n minus phi of n is n minus p minus 1 times q minus 1 plus 1. And p times q cancels out. What remains is p plus q. And also the minus 1 and the plus 1 cancel out. So n minus phi of n plus 1 is p plus q. N is p times q. And again, I assume as well when I was 16 or 17 years old, I learned that if you know the product of two numbers and the sum, then you can find the numbers with a quadratic equation. So in fact, if I have phi of n and n, I can find the factors. So this means that, and you can extend this proof, it's a bit harder. If you know lambda n, you can find the factors. So in fact, whether you can find lambda n or can find the factors, it doesn't matter, it's the same problem. But of course, you could also try to extract roots without factoring. For example, if you apply RSA to 0, well, 0 to the power e mod n, this is 0. Okay? If you take 1 to the power e mod n, this is 1. If you take minus 1 or n minus 1, n is minus 1 to the power e mod n, because e has to be odd. Why? Because it's relatively prime with lambda n, and lambda n is even. So e is odd, so RSA of minus 1 is minus 1. So in fact, I just picked 3 inputs, and they're encrypted to themselves. You can even show that for every modulus, there is 9 inputs that are encrypted to themselves, always. So of course, if you pick a random input, it's never going to encrypt to itself, because the space is big. And remember, n is 2,000 bits or 4,000 bits. You're never going to pick 0, right? It's never going to happen. But if you just dumbly use RSA on a plain text, and your plain text is 0, it's easy to decrypt, because the ciphertext is 0. Okay, so what you have to do is you have to make sure that somehow you map your plain text to a random integer between 0 and n minus 1, and not give the user a raw RSA interface. Right? You have to somehow take the plain text and apply some cryptographic magic that what comes out is a random number. So use randomness and symmetric cryptography for this. If you encrypt a small message, okay, then if m is small, then m to the e mod n is equal to m to the e. If m to the e is less than n, so if my m is very small, and my e, as I told you, people use 3 or something small, this is really bad. So in fact, if my m is small, I can solve the equation using Newton-Raphson. Again, I have to make sure that my m is large, or that I actually apply RSA to random inputs. So a standard was made around 1990 called PKCS number 1 version 1.5, and it does the following. You start with 0, 0, then you have the 0, 2, then you have at least 8 to the random bytes, then you have 0, 0, and then you have the message. And so in many standards, this is what you do, like the Belgian ID card as well. So your message, well, we don't do encryption, but if you would do encryption, we use the PKCS version 1 signature standard. It's very similar. You pad your message with 0 with random bits, and then you put this 0, 0, 2. I looked at this. Does this look like random? So the advice from the cryptographers is map your plaintext to a random string. Well, the string starts already with 0, 0, 0, 2. That's not random. And then it has actually also 0, 0 here. And if my message consists of all zeros, I have more zeros. So it's probably not a good idea to do this. But then the people said, well, this is what we do, and try. If you can't break it, we're not going to change it. This is the mentality on the internet. So then Bleichenbacher came in 96 or 7, and he showed how to break it. More or less what you do is you get a ciphertext you want to decrypt, you change it a bit, you give it to decryption, and you get either a decryption or you get an error message. And from the error message, you can actually learn information, and you keep doing this with many. In the beginning was 10,000, today you need about 1,000 messages. So you take a message, you make 1,000 variants of it, you send it to the decryption, and from the error message you can tell all the bytes of the message. Okay? So the reaction of the internet people was then, okay, we'll not give you error messages anymore, which is really bad software practice, because now you get an error in the encryption and you don't know why, so you just get, okay. So there is an answer. So then the theory people came in, PKCS number 1 version 2.0, 1994. It's still not widely deployed, because people still use version 1.5. It's amazing. And it has a proof that actually you map your plain text to a random string, except that they still use this 02 byte in the beginning, because you want to avoid that your message is too big, right? The problem is if your message is bigger than your modulus, you can't encrypt, so they decide to put something in the beginning. And then a guy came and he showed, in fact, you can also break this, in spite of all the proofs. So today we use CamDem, so we kind of got rid of all this stuff. CamDem means you use RSA like Diffie-Hellman. You use RSA to send a random key. So then you can know your plain text is random, because it's just random. And then you use this to actually encrypt things in AES. So in fact, we give away this property of RSA that you can send a message. We actually just send a random key, and then you use the key with AES. But it took us about 20 years to get there. But you will still find a lot of legacy stuff, even version 1.5. For example, so this is standard from 1990, this is 92. When I was making the specs of the EID card, I said in 99, I don't want version 1.5 in the card for signatures then, not for encryption. And they said, no, we don't have anything else. It's not available. And the card was actually produced in 2004, and I can swear you that the latest version, it's still in there. They still don't have version 2, because it's too hard. Because all these modules have been evaluated, which cost hundreds of thousands of euros. And so unless there is a real attack, they will not do anything. That's how security often works, or fails. So RSA today is not so expensive anymore. Of course, it's hard to imagine, but in the 80s, the R in RSA, Rivest, tried to implement RSA, and he built a chip. He tried to build a chip to implement RSA, and the problem was that chip technology was so small still that he had to first design new chip technology to design a chip for RSA. And so in the end, he had to give up. After 3 years, he gave up to make a chip for RSA. So one of the first chips for RSA was actually built here at the KU Leuven in a startup company, but it was not very secure. It was a 6-chip solution. So on 6 chips, you could put 120 bits of RSA on each chip, and then with 6 chips, you could do 720 bits RSA or so, or 760 bits RSA. That's around 1988, because the computers were too slow for RSA. So today, in fact, people try to optimize many things today. In fact, as you know, you can now put RSA on a smart card that's tiny, it's not such a problem anymore. But so some people had the brilliant idea to give everybody the same modulus, but a different exponent. Now, it's not a good idea, because if you know E and D, you know that ED minus 1 is a multiple of lambda n. And it turns out that you can be used to factor, and then, of course, every user can factor the modulus, and then can find, of course, the D from the other users. So not a good idea to use one modulus for everybody. Would have been very efficient, but not a good idea. So we use small exponents D, but in some applications you want fast decryption and slow encryption. So people had the idea of using a small decryption exponent. Turns out it's not a good idea. If your exponent is less than 29% of your modulus, it can be recovered with some clever math. Okay, so again, optimization, terrible. And the thing is, the funny thing is, if you say, okay, I have a 400-bit exponent, and I have a 1,000-bit modulus, so this is more than 30%, so it's okay. And then your boss says, 1,000 bits not enough, you make a 2,000-bit exponent. Suddenly your 400 bits is no longer enough. Because now 30% of 2,000, you now need at least 600 bits. So it's kind of, we've seen horrible things. Small public exponents, they can be a problem. For example, if you know E minus 1 over E of the plaintext, you can find the remaining 1 over E. So say E is 3. If you somehow have guessed 2/3 of the plaintext, you can find with mathematics the next third, the last third. Of course, if E is large, it doesn't matter. If E is 2 to the 32, then you have to know almost the whole plaintext to find the last bit, and that you can always guess, right? It's not such a big deal. But if E is 3, you have a problem, if your plaintext is predictable. Also, if you send the same plaintext to E users with different moduli, it turns out that you do this, then you can use some clever math to recover the plain text. And again, if E is 3, and say you have a secret key you want to share with 3 users, you send it to 3 users, encrypt it, then if I find all the 3 ciphertexts, I can compute without using any RSA attacks. I just use clever Chinese Mariner theorem. Easy attack, I can find your key. So again, if your E is 2 to the 32 bits, so 32 bits to the 32, you're going to send the same message to 4 billion users because then it's no longer a secret anyway. But if you use small e, you actually are a bit at risk here. Okay, so this is just to warn you that actually implementing RSA properly is difficult, and it has been a real struggle. Okay, so we had to learn how to do this. We had to develop the theory, but also, even if we developed the theory, in practice, people ignored the theory. Okay, and even today, there is still buggy implementation. So once in a while, a researcher takes all the smart cards and crypto modules and whatever and tests all the attacks we know, and they still apply to some of the modules. Even models with a common criteria certification. To give you one example, there was some Czech researchers who were looking at RSA public keys. And they found some strange structures in there. And so they did the research and more research. In the end, they found out that the key generation somehow made sure that they could only use very few primes, and you could more or less factor the moduli, because you could kind of predict the primes. And so this was a chip from Infineon, and the key generation had been approved by a German certification body, who put a big stamp on it, approved, but in fact it was a terrible key generation. And then the more interesting story, if you understand crypto politics, so the Estonians, they're the digital society. Everybody has an ID card, like in Belgium, but they use it even more, also for their elections, which is a terrible idea, but anyway. But so the researchers informed Infineon in February, and the Estonians had elections in October, but nobody in Germany bothered to tell them. So they were only told by the Germans 4 weeks before the election, by the way, all your keys can be factored. Oops. So in cryptography, you know who your friends are. So it's again a warning how things can go bad. Okay, so now Diffie and Hellman. So Diffie and Hellman were a bit frustrated because they couldn't do encryption. Although we now know we don't do encryption with RSA anyway, we do CAM-DEM. But still, they wanted to do encryption, they couldn't do it. They got a brilliant student, El Gamal, and he actually found out how to do it. It's embarrassingly easy. Once you see it, they say, oh yeah, of course. But I guess they didn't see it. And it's easy to say after the fact, of course. So the idea is that Bob has now a fixed private key y and a public key alpha to the y mod p. So Bob doesn't choose a random y every time. He has now a fixed y, which is his private key, and his alpha to the y is his public key. Okay? So Alice will generate an x to compute alpha to the x mod p. Alice can now generate the key alpha to the y to the power x mod p. So she now has a key. What she will do is she will actually multiply the plaintext with this key to get the ciphertext. And that's it. Of course, you have to make sure the plaintext is not 0, because then the ciphertext is 0, but that's it. Right? You just make a Diffie-Hellman key, but with the Bob side fixed, and then you actually use it to encrypt. You can also use one-time path. You can XOR, or you can multiply. But people prefer multiply because then they stay in the group. You can multiply the key with a message. And so you can send this to Bob. So you send to Bob alpha to the x mod p, like in Diffie-Hellman. You send it the ciphertext. And what will Bob do? Bob will compute the Diffie-Hellman key, take what he gets from Alice alpha to the x, raise it to his secret y, and then divide out the key. Okay, and then he finds the message. The egg of Columbus, but Diffie and Hellman didn't see it for 10 years. They had to have a bright PhD student who told them how to do it. But of course, very often with brilliant things, it takes a long time. By the way, there is this story which nobody can prove, but so GCHQ, the British Secret Service, they invented the concept of public key in 1967, a guy named Ellis. But he decided to keep it secret, even when Diffie and Hellman published their paper. And then Ellis asked every 5 years, can I now make it public that I did this before? And they said no, until Ellis died, and then they made it public that Ellis had invented public key 8 years before Diffie and Hellman. So this is why you shouldn't go work for the Secret Service. And then there was another guy, Cox, was a mathematician from Cambridge, and he joined GCHQ. And apparently somebody told him over lunch, so maybe I should tell you first something before. So Rivest and Shamir, they give great talks how they looked at this problem, and it took them 3 months to find the RSA algorithm. Right? They had to try all possibilities, and they tried this and that, and after 3 months they finally found the RSA algorithm. So Cox came to GCHQ, I joined in the morning, he had a conversation with somebody over lunch, and by the evening he had invented RSA. He actually walks around and he gives talks now. He's a very nice guy, very friendly guy. But so he must be a real genius, right? I mean, that 3 people took them 3 months, he did it just in an afternoon. But again, he was not allowed to publish until 1997. So they can also have made this up, right? We don't know the stories. You have to believe the GCHQ. Who believes GCHQ? I don't know. Anyway. But so it's a simple idea. But more or less, if you look at textbooks, they will use this notation. I'm not going to go through it. It looks much more complex, I find. But if you just, what I do is I just use Diffie-Hellman notation. First explain Diffie-Hellman, and then this is very easy. But the point I want to make is if you then introduce special notation only for El-Gamal, it becomes very convoluted, and how do we get there, and so on. But so this is more, if you see it in a textbook, you will see these letters and symbols. And I find it kind of hard to see the connection with Diffie-Hellman. It's the same system. So El-Gamal relies on discrete logs, so you can use it to elliptic curves, and this is kind of widely used. It's called ECIES. This is a way to elliptic curve encryption system. So if you look at Diffie-Hellman, so RSA is a permutation, so you take a space of 0 to n-1, and you map it to 0 to n-1. El-Gamal is a bit more annoying because you start with a plain text mod p, and the result is 2 numbers mod p. Okay? So you have to send alpha to the x and c. So suddenly, if you want to encrypt 1,000 bits, you now have a ciphertext of 2,000 bits. Plus, you have to generate random numbers. Okay, in RSA, you don't have to generate random numbers. Well, you should to randomize your plain text, but in fact, here you really need to generate random numbers, otherwise you have a problem. So, on the other hand, it's actually good because we can show, so you have to need random numbers, we can show this is probabilistic encryption, and in fact, if you think about it, secure public key encryption always has to be randomized, because you get a question and you answer yes, you encrypt with RSA, okay? And then you give another question, you answer yes, you encrypt with RSA, you get same time the same plain text, you get same ciphertext. So in fact, all secure encryption has to be randomized, which means that you have to use some random bits to mix your plain text before you compute the ciphertext. This is for the case for public key and symmetric key. If you really want good security, you have to run randomized encryption. To prevent that, the same plain text gives rise to the same ciphertext, and you leak information that, my answer was yes 2 times, or was equal 2 times. Of course, if you randomize your plain text, you need more space, right? In RSA, in fact, I kind of glitched over it, but we looked here. If you look at PKCS, where was PKCS here? Also here you have randomized encryption. This PS is a random string. So if you encrypt 2 times the same plain text M, you get different ciphertext because this PS pseudo-random bytes have to be different again. Right? So it's a very common practice to do this. But so this means that, of course, if you have to have at least 8 random bytes, this means that you cannot use those bytes to put plain text. So you lose them. So these random bytes somehow have to be sent to the recipient, so they cost you extra overhead. That's the price to pay for it. But it's definitely seen as good practice now. So as I showed you, RSA and El-Gamal are like 1,000 times slower than AES or so. So it's only used to encrypt pins. So if you use a credit card and you type your PIN in a terminal, it's actually encrypted when it's sent to your card to prevent tapping of the PIN in the terminal itself. Of course, the terminal has your PIN because you typed it, but they want to protect the line that people have been caught tapping the line between the smart card and the terminal, so you have an encrypted PIN. But in most cases, as I said, we use CAMDEM, which is CAM stands for Key Encapsulation Mechanism, and DEM is Data Encapsulation Mechanism. So DEM is a difficult word for authenticated encryption, which we discussed already briefly. We'll discuss it more in detail on Thursday. So it's typically a specific mechanism or an encryption mode plus a MAC on the ciphertext. That's a DEM. And so the CAM is just a way to send a random key over. And this is what everybody now uses today. And it's very rare that you use public key to send a message over. So these hybrid systems are widely used. So if you look at TLS, IPsec, which is VPNs, SSH, EMV specs, email encryption, all messaging, they all use this CAM-DEM mechanism. So this is now the common way of doing things. And so in some sense, PKCS #1 version 1.5 is disappearing not because it's being replaced, but the new people use a different approach, completely different philosophy. So I already showed this to you, this CAM-DEM mechanism. So you first generate a key. It can be two keys if you have an encryption key and a MAC key. You can also have to take an encryption mechanism with one key, but that's your session key. So you use it to encrypt your message, and then MAC the ciphertext with the second key potentially. And then the public key system is used as a CAM, so it's just only used to transport a random key. And this makes many attacks harder because the plaintext is random, will be different every time, so many attacks don't apply anymore. And then at the other side, you will decrypt, get the session key, you will get the MAC key and the decryption key, you check the MAC. If the MAC is incorrect, you stop decrypting. You don't decrypt and you don't output to protect your encryption algorithm and decryption algorithm. And if the MAC is correct, you actually do decrypt and you output the plain text. So this is more or less what's happening today. So it's slightly more expensive because if you think of RSA, if you use like 2,000 bits, you only send the key. The error key is 256 bits or so, an AES key, 128-bit, 256 bits. So in fact, you waste all the rest. You could actually put some message in there, okay, and save space. But kind of people don't bother anymore. If they want to save space, they use elliptic curves. And there the space is short anyway. So the keys are 256 bits. And you waste 256 bits because the doubling in El Gamal, you have the double size. But that's okay. But in fact, in RSA, if you use CAM-DEM with RSA, you waste thousands of bits, right? But nobody bothers about this. In many applications, nobody cares about a few thousand bits today. It just still matters in smart cards or small devices, but in general, nobody bothers. So in practice, you have to do still key management. But of course, with a symmetric key, you have n times n minus 1 over 2 key pairs. But in practice, in symmetric key, you have, as I explained to you, a sample party like your GSM operator that owns all the keys. But in public key, you can have a decentralized offline party. So security depends on mathematics, which is nice, but there could be problems. And the cool thing of public key is you can do other stuff like eCache, voting, and auction. If you have these structured problems, you're more vulnerable to quantum computers, so they also apply to symmetric key, but it's easy to defeat, and anyway, I don't think they apply as much, because these need huge quantum computers for symmetric key, but for public key, there is a huge problem. I already showed you this picture. This is the first 7-bit quantum computer. This is, in fact, Lieven is now a professor in Delft. He studied in this department in mechanical engineering here. Then he got a PhD in Stanford. So he programmed the first quantum computer, and he spent 4 years to factor 15. And he got a PhD for that. So IBM is the only ones who make a roadmap. So many companies, Google, Intel, and so on, they're investing massively. IBM is interesting because they make a roadmap, which is also interesting is that Osprey is 433 qubits. It's from last year, but the details have still not been made public. So we doubt whether it actually works. Okay, so we still haven't seen the details of Osprey, and we're already almost at the end of 2023. So I doubt whether we'll see Condor in 2023. And you also see from 2024, they say beyond. So there is no more predictions. So, and then anyway, what they show you are physical qubits, and you have to implement error correction to get logical qubits. And so RSA 2048 requires 4096 logical qubits, and we think, we don't know because it will depend on how the computer is built, it will require 20 million real qubits. So we're not there yet. I'm not waking up every morning, has the computer arrived? Because it's still not clear whether Osprey has arrived. From 400 to 20 million. It took us 3 decades to go from 2 to 127. So from 400 to 20 million may also take 2 decades. So when to switch, you make your guess how long it takes to build your computer, how long it takes to switch, and then how long your data has to be confidential. And then you had the formula, which is Moscow's formula. You have to switch in 2023 plus Q minus X minus Y. So if Q is 15, so you think that they will not be done before 2038. If it's 5 years to switch and you need 10-year secrecy, you should actually start switching today to new algorithms. So you're already too late. And the NSA, they're way too late because they have 50-year secrecy requirement. Because if you do many illegal things, then you want it to be hidden forever. So they want things to be secret for 50 to 100 years. So they already should have switched a long time ago. They're the most pushy. They now want to be done in 10 years with their complete conversion. And now the banks get nervous. They also want to be done. Maybe they also have illegal things. I don't know. But I don't think there is such a rush. But still, we have to start moving. This is for encryption. For data indication, in fact, you can change on the spot. So you can change when the computer is there. Then you can change the day before. This is still OK. You can take a bit more risks. Because if your signature is broken tomorrow, if you resign today, it's OK. Right? So the problem there is different. There was a competition like the Olympic Games for cryptographers. Started 2016. It ended this year, but then decided to keep going for 2 more years. But so what you can see is that they got 89 submissions in many variants. In the end, they chose 2 lattice-based schemes and 1 hash-based scheme. And then IETF independently already standardized 2 hash-based schemes. So more or less, we tried many different techniques, but we ended up with actually hash-based schemes, which are from the 70s, and lattice-based schemes. This is kind of the only innovation. There is only 1 encryption scheme standards and 2 signature standards chosen for now. And they're looking for new encryption schemes in this category here. There's still an ongoing competition, extension for new signature schemes and encryption schemes looking at here, because this is a bit worried that everything depends now on these lattice-based problems. But so you will hear about Kyber in the future. Kyber is the public key encryption, and Dilithium is the public key signature. Falcon is, you will not hear about it because you can't specify it and you can't implement it. I don't know why they picked it. But they now said that they still need another 6 months to write a standard, although this algorithm is known already since 7 years, and they still don't know how to write it down. And the developers have apologized, designers, for the algorithm because it's so messy. So I don't think it will become very popular. But I think these are 2 names you have to remember, Kyber and Dilithium. And then for hash-based signatures, Sphinx, Latin Mikali, and XMSS. So this is what people are rolling out today or looking at today. So if you join a company in 2 years, they will say, do you know about Kyber? Can you make sure we implement this here? It will be a challenge because this is public key size in bytes. This is ciphertext size in bytes. ECC is like 80 to 128 bytes. It sits somewhere here. So it's 512 bits is the biggest one. So 64 bytes may be enough even. RSA sits here. And Kyber and Dilithium sit here, right? I mean, Dilithium is a signature algorithm, but like, huge ciphertext and huge public keys. And for some applications, it doesn't matter. For some, it's going to be dramatic. Okay, and then of course, there were other stuff which was even worse, like people are still looking at code-based cryptography, where the public key is 0.5 megabyte. So this is for cryptography back to the 80s, when it's very hard to implement stuff. In terms of performance, this is not cycles per byte, this is operations per second, so the higher the better. So surprisingly, this is comparison to RSA and ECC. Kyber is actually faster than everything we have. So public key encryption becomes faster, but the keys and the ciphertext are huge. So for some settings, it will be a nightmare if you have small devices, small storage, contactless interfaces. It's a problem, but in fact, because it turns out the public key operations are not cubic, they're quadratic here. So the public key is quadratic, and the operations are quadratic. In RSA and ECC, the operations are cubic, but the keys are linear. So you kind of get a different trade-off that will be very painful, and I think your generation will have a lot of fun for the next 10 years to integrate all this in new implementations. Okay, time to stop here. So see you on Thursday. On Thursday, we speak about data authentication.